Problem 2. A sheet of BCC iron 1 mm thick was exposed to a carburizing gas atmosphere on one side and a decarburizing atmosphere on the other side at 725 degrees centigrade. After having reached steady state, the iron was quickly cooled to room temperature. The carbon concentrations at the two surfaces of the sheet were determined to be 0.012 and 0.0075 weight percent. Compute the diffusion coefficient if the diffusion flux is 1.4 into 10 to the power minus 8 kilogram per square meter second. So in this problem we have to find the diffusion coefficient. Coefficient. Okay, so we know that the diffusion coefficient is represented by D, and further we assume that there are steady state conditions for the diffusion. So we can write the diffusion flux equal to minus D, okay, and then C2 minus C1 divided by delta X. So where C2 is the concentration at the high pressure, C1 is the concentration at the low pressure. Okay, two surfaces. So the concentration values in these equations are in kilogram per cubic meter, but the concentration values which are given over here are in terms of percentage weight. So we need to convert these percentages, weight percentages into the kilogram per cubic meter. So since this is a carbon and iron compound mixture, so we can convert these weight percentages into the kilogram per cubic meter by this formula. So actually we need to, according to the notation which we are using, so we need to convert the percentages into the kilogram per cubic meter by this formula. So we use a notation which is called as which is C double prime, which is in kilogram per cubic meter. It is equal to C1. So for example, if we take a carbon as the first, if we denote carbon by number 1, so it should be C1 over rho 1 plus C2 over rho 2. Okay, so this will, and then you multiply it with 10 to the power 3. So this will be the concentration in kilogram per cubic meter, and here C1 and C2 are concentrations in weight percentages. So for this equation we need to know the rho values, which are the density values. Okay, so rho 1 is the density of carbon. So from the information on the tables or the internet, we can find that the carbon has a density of 2.25 gram per cubic centimeter, and the iron has a density of 7.87 gram per cubic centimeter. So what we can do is we can input these values over here. So for the first case, so we can put a value which is equal to for 0.012. okay, so 0.012 percentage weight divided by 0.012 percentage divided by rho 1, so it should be 2.25, and plus C2 will be 100 minus 0.012. okay, So C2 will be 100 minus 0.012 divided by density of iron 7.87 multiplied by 10,000. So it is equal to 0.944 kilogram per cubic meter. Okay, so this will be our value C2 in this equation. Okay, C2. Well, these C1 and C2 are only for that condition. Okay, so I think it may be better if I used over here carbon. Okay, anyway, the other value in kilogram per cubic meter corresponding to this value can be also found. So that will be C2 C1 prime again. Okay, so this will be equal to 0.0075 divided by 0.0075 divided by 2.25 plus 100 minus 0.0075 divided by 7.87 multiplied by 1000. So it is equal to 0.59 kilogram per cubic meter. Okay, so anyway, so now we know that 0.59 is the value which you will use in this equation for this C1, and 0.944 will be the value which will be used for C2. So just input the values into this equation. Okay, so J is 1.4 into 10 to the power minus 8, and minus D we need to know, and this is 0.944 minus 0.59 and divided by delta x. Delta x is this 1 millimeter thick plate, so it is 1 millimeter thick, so into 1 into 10 to the power minus 3. So from here the value of D we can find out as equal to 3.95 into 10 to the power minus 11 square meter per second. So this will be the value. Well, one minor point maybe that someone would say that the answer should be negative over here, but in fact I missed one point to tell that, because this delta x distance is like this. Okay, so for example, if you take an x direction as this, so this delta x distance is, this is the position 2, okay, and this is the position 1 corresponding to this higher and lower concentration. So if our positive x direction is towards this direction, so this value we will take from here to here value. So if we take this position as 0 and this position as 1 millimeter, so we are basically taking delta x is equal to 0 minus 1, so it is minus 1 millimeter. Okay, so in here we can use a negative 1 millimeter value over here, so minus sign will cancel out, so the answer will be positive.